Welcome! In this lesson, we'll cover different types of chromatography techniques that are often used for radionuclide separation and quality control. Chromatography is a technique used to separate compounds in a solution, or mobile phase, based on affinity with the stationary phase. This stationary phase is commonly placed in a column with a filter on the bottom to retain the stationary phase. The solution containing, for instance, the target ions and product radionuclides is then passed through the column containing the stationary phase. Depending on your choice of stationary phase, either the target or product nuclides will be retained on the column material, while the other doesn't interact with the stationary phase and passes through. There are two general types of chromatography that we can distinguish. Planar chromatography uses a thin layer that is supported on a sheet, which can be either glass, plastic, aluminum, or paper, for example. You might have tried this yourself in the past, using planar chromatography to separate the different colors present in ink. Column chromatography is much like the example we just discussed. It uses a tube or column to retain the stationary phase, after which the mobile phase is passed through using either pressure or gravity. Commonly used chromatography methods in radiochemistry are thin layer chromatography, or TLC, high performance liquid chromatography, or HPLC, ion exchange resins, and inorganic resins, although more exotic options do also exist. Of these, TLC or ITLC are planar chromatography methods, and all the others are column-based chromatography methods. Thin layer chromatography is often used in radiochemistry as an easy, high-throughput method for quality control of your sample. For example, to determine the radiochemical purity and labeling efficiency of radiopharmaceuticals. The radionuclides that are bound to the drug will interact with the TLC paper differently than the radionuclides that are still free in solution. The TLC paper itself consists of a solid phase, for example silica gel, which is attached to a thin plate or paper. A small drop of the to-be analyzed solution is spotted a bit above the bottom of the strip and then allowed to dry. The strip of paper containing the spotted solution is then placed in a container with a small layer of solvent, the mobile phase, on the bottom. In time, the solvent slowly moves up the paper, moving over the sample spotted on the TLC paper. And based on the affinity of the compounds in the sample with the solvent and the stationary phase, they either move up with the solvent or they stay at the bottom of the paper. When the solvent front is close to the top of the TLC paper, the paper is removed from the container and dried. The different compounds in the sample will have separated from one another, as they move up the paper at different rates. When analyzing the radioactive spots on the TLC paper, you can calculate the retention factor by dividing the distance the sample has traveled on the paper by the distance the solvent has traveled. The RF value is therefore always between 0 and 1. HPLC, or high performance liquid chromatography, works by passing the mobile phase through a column containing the stationary phase, using high pressure pumps. The stationary phase will interact with the different components in your sample differently, retaining some longer than others. And a detector at the end of the column detects these components as they exit at different times. Similar to TLC, HPLC is mainly used for quality control, but it's a much more sensitive method than TLC. For example, it allows you to determine the radiochemical purity, specific activity, and stability of the radiopharmaceutical. Next to quality control methods like TLC and HPLC, chromatography is also frequently used to separate the product radionuclides from their target materials. Ion exchange resins are most often used and known for their very high separation factors and ease of use. These resins are packed in a column, which can be either very small or very large, depending on the amount and type of materials you need to separate. They consist of, for example, a cross-linked polymer matrix. The matrix contains functional groups that are able to exchange ions depending on their binding affinity. In this example, you see that sodium ions are exchanged with calcium ions. However, one challenge with ion exchange resins is that they are not very resistant to radiation, and they are known to break apart at higher radiation levels. For these situations, inorganic resins are ideal. They are cation exchange-based sorbent materials and are stable even in high radiation fields. As a downside, these types of resins are often less selective than the organic ion exchange resins. On the right-hand side of the slide, you can see a microscope image of an inorganic resin particle. Probably the most famous inorganic resin in the field of radiochemistry is the alumina resin used in the molybdenum technetium generator. Finally, if we want to quantify the extraction behavior of a column material, we generally talk about the distribution coefficient. This is defined as the concentration of the ion of interest that remains in the stationary phase, so with the column material, divided by the concentration of the ion in the mobile phase. A high distribution coefficient then means that the ion has a high affinity for the resin material. As you can see in the image on the right, the Kd can vary greatly with the pH of the solution for the different lanthanides in this case. And changing the pH of the mobile phase is therefore an often used approach to sorb and desorb the different ions to the column material. Let's look at an example. Say that you have irradiated a zinc target material to produce copper-67. You want to use a column material for the separation of these two metals, and the Kd values for this column material are displayed in the figure. How would you use this column to separate the two metals? You see in the figure that at higher acid concentrations, copper has a much higher Kd than zinc. This means that at these concentrations, copper will sorb to the column, while the zinc will simply flush through. By first washing your column with, for instance, 5 molar acid, you make sure only copper remains on the column. And then you can decrease the concentration of your acid to, for example, 0.01 molar, where also copper has a low distribution coefficient, to then extract your copper. As you've seen in this lecture, chromatography is not only very important for the separation of radionuclides from their target materials, but also for the quality control afterwards. Next lecture, we'll look at another separation technique, solvent extraction.